Good morning, everybody. So this is the welcome to the final workshop of this trimester in IHP, and this final workshop is both the final workshop of the trimester. It's also a final conference of a certain grant, the ANR, a grant French in France around the similar topics, VAL-COMO, valued fields combinatorics model theory. So, and the conference will represent these themes, but also general model theory together with applications. So the first talk is by Ehud Hrushovski on a tour of globally valued fields. So welcome to give the first talk, Ehud.
Thanks very much. Hi. Yeah, so this is going to be a very soft introduction to something I've been thinking about for most of my career, about 30 years. Recently, meaning in the last 10 years or so, have been working on with Itai since it became clear that it's best to do it in continuous logic. I thought I would, this is the 100th anniversary of Abraham Robinson, and I'm looking forward to a talk by Lau about him. But since this is a very Robinsonian subject, I thought I would also say a few words about the influence of his work on me, in particular on this. It's never been a direct influence. When I was doing my PhD, it was somehow, I was doing stability theory, and this was, I mean, somehow East Coast model theory had nothing to do with it. But I ended up doing some East Coast model theory. And it's not that I ever exactly read Robinson, but more that somehow ideas developed over years of doing practical model theory. You go back and you see that Robinson had these ideas very, very clearly in the very beginning, and in the very beginning of, well, logic almost, 20 years after Gödel's theorem or less, of modern logic. So, I mean, it's very likely that, in fact, his ideas were somehow dispersed and scattered and then come back when you actually do model theory. What model theory is influenced by these ideas. So I'll mention a few things. On a technical level, here's the first one to study valued fields along with Tarski had already, I think he independently studied algebraically closed fields and maybe real closed fields, but Tarski did that earlier, but he added valued fields, which are going to be a key technical ingredient of what I'll be talking about. So globally valued fields, well, in particular, there are valued fields, and you try to add another ingredient, which is global. This title I really love, On the Metamathematics of Algebra. Later, he published a book in which he added the words model theory to the title. And to me, it's a privilege. So algebra was maybe out of modesty in some sense, at least later. He certainly also contributed to analysis. I'm not thinking so much about non-standard analysis, but to the actual theorems he proved. Well, about compact operators, various theorems in analysis, clearly, or in partial, clearly not thinking that it's restricted to one area. But what he did realize is that despite Gödel's theorem about all of mathematics, the situation is quite different if you try to describe the metamathematics of large part of mathematics. It's not the same. All of it, which cannot be somehow axiomatized satisfactorily, and very large parts of it about which you can learn quite a lot by choosing the right domains and axiomatizing them and trying to study them. So I really, later people struggle to define what model theory is, but I think he had a very, very clear vision very early on. So what does it mean, metamathematics of algebra? I mean, he emphasized both a historical role going backwards. I think I have the impression it was important to him, and a forward role. In other words, that some of what you do may lead to new theorems or to indicate new theorems or new kinds of theorems. And in fact, and I think that's right. In other words, the present is a somewhat arbitrary dividing point. You shed some light on the subject, And part of the interest in it is in understanding the history of the subject. And from time to time, you know that you're doing something non-trivial by actually getting something which has not yet been done. My first experience with this was with differentially closed fields, which he also started the model theoretic study of. And it was really amazing for me when I knew absolutely nothing outside of stability theory to see how you just take the logical axioms, you just take the Leibniz law, and then you develop model theory. You do what you have to do. You do what Robinson tells you, that you look for a model complete theory, and then you do what Shelach tells you, that you have to look for stability phenomena for regular types, and you end up rediscovering an unbelievable amount of classical mathematics, in that case essentially 19th century theories of a billion functions or a billion varieties or whatever. Yeah, so the goal in this talk is the following realization, which somehow I've been interested in for a very long time. This thing has been very successful for differential fields, for algebraically closed fields, for local fields, but all of it, essentially, all of the theories accessible to model theory have been local. So there's a description of areas of geometry and number theory, which is somehow 19th century, but became very clear by the first third of the, I don't know, by 1940 to André Weil, let's say, with distinctions between local behavior, such as, I don't know, derivations and so on, and global behavior. So globally you understand, let's say, a manifold by understanding it locally at every point, and then there's a little bit more. Yeah, there's somehow, there's also a global structure which influences it. And essentially all of the known model theory is either generic, which is even somewhat less than local, or local. There's nothing about global geometry, except negative theorems, yeah, like undecidability of Q, undecidability of certain function fields, and so on. But it's clear that mathematicians are pursuing, if you look at the history of mathematics, it's clear that there's also a positive theory there, and the goal is to discover it. I mean, to give a model theoretic account of why they're also, why it's possible to prove quadratic reciprocity, why it's possible to prove, to do things in global geometry. And somehow what is the analog of Leibniz's law? The analog should be the product formula. This is the thing that ties together the different valuations. This is the prime number theorem. It ties together the different primes, including the prime at infinity, as we're told. And well, if you think about geometry, it's the rule about zeros and poles of a function adding up. And once again, okay, so in some sense it's just the beginning of this activity, but in fact, once again, pursuing even the basis model theoretically leads to seeing completely new parts of mathematics. So I'll try to explain a very small amount of that. Some of them are still, very mysterious to us. We're getting there slowly. And okay, so I'll say something about what one sees when one tries to do this for the product formula. And I should mention that, that maybe probably the first model theoretic paper to look at the product formula is, again, Robinson's. Later, there was a paper of Robinson and Rouquette, which is very well known, and in which, in particular, well, he talked about transfer principles, how model theory can take ideas from one area and move them to another area, which is best known around Axe-Coach and local fields. But in fact, he tried to do it for the connection between arithmetic and geometry. So he tried to take alter powers without any model completeness theorem available at this point, and to relate divisors over function fields and number fields, and I'm going to emphasize that point in a modern version. Okay, so for me this started about 30 years ago with listening to a talk by Lau van den Dries about the algebraic integers, where the description that comes out is the following thing. We try, so we have an algebraically closed field. And if we have the algebraic integers, then in some sense we can, we can look at things modulo 2 or modulo 3. Then modulo 2, we don't have a single valuation. We have a whole compact space of valuations, all the ones that lift the two-adic valuation. But somehow we're able to discuss it. We're able to discuss this compact space by talking about the associated Boolean algebra. And you end up with some structure like this. You have a field. You have a Boolean algebra. Sorry, this is too early, the reals here. Forget about this reals. But you try to talk about all valuations by talking about the stones, by talking about the, by thinking of that the space of valuations is a stone space of some Boolean algebra. There are some technicalities I'm not going to get into here. And you think of a kind of Boolean valued field. In other words, for every formula of valued fields, it's not going to be true or false exactly, but it's going to get a truth value. The truth value you can think of as a set of all valuations, such that if you look at Q bar with that valuation, then for that it's true. So for instance, the fact the valuation of 2 is bigger than 0 is going to be true for all these valuations lying over 2, and not for the other ones. And the guiding principle for the completeness of this theory is complete cut and paste. Again, I'm not going to say it technically, but it's unrestricted, partly because you've thrown out the real prime. If you want to give some description of something modulo 2 and then another description modulo 9, they're just compatible. You can basically do what you want. So this is gluing principle. You have a lot of valued fields, and you can glue things together. And all right, so this is already a great step towards global things. But there are two tasks, there are two things missing. First of all, we know that, if you have one hole, then somehow a container with one hole is completely different from a container with no holes. Yeah, after that, it doesn't matter how many holes you have, things fall out. So principles, so you don't see anything global unless you have all the places. So one task is to add the missing prime, which in this case is the prime at infinity. Or if you do a function field version, it's not good enough to look at the affine line. You have to look at the projective line. And the second thing, now R really does come in, is that we need a way to talk about heights. We need a way to talk about many primes. So the prime number theorem, you cannot state it in terms of one prime. You need to talk about all primes that may divide something. And the product formula is formulated in terms of a function into the real numbers. In other words, the sum of the p-adic valuations over all p, including infinity, should be 0. So you need some kind of sum or integral. Okay, and I first made some attempts to see it as a first-order theory. There's no way. It's going to be undecidable as a first-order theory, and we have to go to continuous logic, which by 10 years ago, let's say, had become very, very well developed. But so I hope everybody feels very comfortable with it now. But in case you don't, you can just think of it as adding one more sort to the structure. So you have the field, and you have the thing that receives the integral, which is the real number. So you can think it's a real closed field. But you add one condition. You add the condition that you only care about models where this sort is exactly the real numbers. Okay? So it sounds like some kind of omitting types conditions or something like that, but it's much better. It's a locally compact situation, and I'm going to explain in a minute how you can take ultra products or your favorite way of doing compactness, and it's still going to be true for this class. You take the ultra power, and then you restrict back to the usual reals in a certain sense. So essentially all of model theory works, even though it was very beautiful work of many people to show that it works, but essentially everything works. Yeah. However, okay. Right, and I'm going to go right into the basic formulas and I'm going to give as examples. So the idea is, as I described for the algebraic integers, namely, you can say what you want locally, but then the formula does not give you a truth value. It gives you, well, maybe in some sense where it is valid, but better, it gives you a kind of expectation of this formula. If the formula even gives you local, it may even locally give you real numbers, and then what you get globally is the integral of these. So the example I took is the following. Suppose you take affine n space, okay? So algebraically, you have polynomials in n variables. And you have some subvariety of that y, and y is going to be cut out by k polynomials, right? So locally, if you just look at the expression here, for a given valuation, this is somehow a reasonable measure of the distance to this subvariety. So if you take a point which is not in y, well, to say that to say that a point is in y is to say that all the fi of x's vanish, which means they have infinite, the valuation of that is infinite. And if it's very large for every single fi, then that means that you're very close to this variety. So this is some kind of measure of local distance. And if you're not used to it, this differs by a logarithm and a minus sign from the usual notion of absolute value. So if your valuation is the usual Archimedean valuation, which I'm allowing, then by v of x, you should here minus log of the absolute value of x. So first of all, it's logarithmic. It's an additive thing. V of xy is v of x plus v of y. And secondly, there's a sign reversal, which is infinitely confusing. So big means close. So big distance means close. Okay. But this is, okay, it's a confusing triviality. There's actually, well, it's impossible to keep track of the sign because there's about 3 different ways it changes. But anyway, okay. All right, so this is locally. And then the global thing is, in some sense, some kind of mean distance. In other words, you don't get, well, you don't see it at one place, or rather you see the expectation that it holds. It's not literally an expectation. More typically what happens is that at all but finitely many points in the classical models, you just get 0. It's somehow just not on y at all. It's not close to y. And infinitely many other points, it has various distances to y, and you get the sum of these things. And I should say that even though I denoted it by the ideal, it's not correct. It actually depends on the choice of generators. In the function field version, which, well, okay, in the function field version, it doesn't, then it is correct. And in the number field version, the coefficients do matter. Also in the function field version, we are not over the constants when you're over a non-constant function field. So the coefficients do matter, and there exist ways to mitigate this. So there exist many questions reduce, well, important questions do reduce to a billion varieties, and on a billion varieties, there's something called the canonical height, which no longer depends on that choice. So it's a nearby, it's an improvement of the height in some sense. And so it's a very classical theory going back to, well, the middle and the early part of the 20th century at least. And in fact, it will shed a lot of light on quantified free types, as we will see. Okay, and one example of this, if you just take the affine line, it happens to give you what is called the height. If you take the distance from 0 or something like this, it gives you the height. So when you have the product formula, there's a discreteness built in to the situation. It's like the situation with z. If you're not equal to 0, you cannot be close to 0 everywhere. Any integer somehow has a discrete distance from 0. So in a globally valued field, the integral of the valuations will be 0, which means if it tries to get close to 0 in a few places, it will have to pay for that by getting far from 0 in some other places. However, in this height, we ignore the places where it's far away. We take only the positive part of the valuation, and then, okay. And then it is possible, so, I don't know, 2 to the 100 is duadically close to 0, and it's going to have large heights. Yeah, it's a measure of how big, in some sense, the number is. Okay. It's possible to just write down the universal axioms, and the product formula plays a big part, but I won't do it. I will just instead describe a class of structures whose universal theory is the universal theory GVF. So let's take a curve over an algebraically closed field. And the field we're interested in is the function field. Okay, so an element of this, of a variety x with coordinates in the function field can be viewed geometrically as a map from the curve into x. Okay, so you have x, and inside of it you have a curve traced out. You can think of it geometrically like that. Sorry? X is any variety. If you like, you can think of an over little k. Yeah, you can do it over big K too, and then you have to think of sections. Let me just take the affine. If you want to take X to be projective space or all of affine space. Okay, so we have some ambient variety X, which is maybe affine space, and maybe we have also a subvariety Y, and then we have a point which is actually, the point A is actually, you can think of it geometrically as a curve. And of course, the point of view of function fields already exists in algebraically closed fields, but then if you think of a curve as a point of X in the function field, what can you say about it? Well, essentially nothing, right? I mean, it doesn't take much to give the generic type in ACF. You can say whether or not the curve entirely lies along the subvariety. Probably let's think of the subvarieties being codimension 1, X maybe is bigger, and C is a curve. Well, you can say whether C lies entirely on Y or not. But just pure field theory it cannot tell you any local thing even. It cannot tell you whether the curve intersects. No, that's not true, Itai. You're in, what? You're thinking about something else, yeah? Okay. All right, so in the pure field language, you can just ask whether your point entirely lies on Y or not. There's nothing else you can ask. In the valued field language, you can do a little bit better. So a valued field corresponds to, so we said that K was the function field of C. Well, if you view it as a valued field, it means that there's some particular point, let's say it's evaluation at some point 0, and so there's a particular point that the algebra is able to talk about. So in that case, that's a little bit better. You can talk not just about the question whether the curve is entirely on Y, you can also ask whether your one special point that you can discuss lies on the intersection or not. Or a little bit better, you can ask how much it lies in the intersection. If it has valuation 0, it's not there. And if it has bigger and bigger valuation, it means that the curve intersects Y with bigger and bigger multiplicity. But it's still not global, right? So now we've got into local algebra, but okay. But suppose you want to know about really global properties, not about one point, but the general question of whether it intersects or how much it intersects at all. What is the intersection number? So this is what the GVF language can tell you, namely, there's an additional data that you have to give. You have to give a real number, a positive real number, which is the mass of any given point on the curve. And then a typical GVF formula will tell you how many points are in the intersection of C with Y. Okay, so this is the kind of thing we're trying to capture. And there's an important remark here that I made C look very smooth, but it's the wrong picture, because we're trying to go up to the algebraic closure. So we're not actually going, we don't expect to understand the theory of K of C. That is Gödelian. We hope to get something more decidable by going to the algebraic closure, by taking larger and larger and larger finite covers. And when you do that, this picture of a curve is completely wrong. If you're in projective space, you're in some kind of compact space, and you take a very large degree curve, it probably just somehow goes all over the place. If you take an epsilon thickening, you're going to get everything. Yeah. So a much better picture is that, well, you should imagine C just running all over, and maybe there's some reason that it avoids Y, but then there has to be a good reason. And if it intersects Y, well, there's going to be probably a large finite number of intersections, and to each subvariety, at least let's say to each codimension 1 subvariety, you can assign a number which is, well, R multiplied by the intersection number, which is a kind of measure on subvarieties, right? Measure on at least codimension 1 subvarieties. That's what gives you the GVF structure. Yeah, when you take larger and larger degree, the weights are adjusted, so it behaves a bit like a measure. Yeah, I mean, you get a very large number of points, but then when the degree is higher, you count them less and less, so it might kind of converge to something. Okay, in the number fields case, well, you take a finite extension of Q. This is the classical case. And above any rational prime, you may have finitely many different valuations on your field L. Let's say it's a Galois extension of Q. Then all the valuations over a given P are conjugate to each other by the Galois group. And then you can play a game which makes it nice to visualize. Instead of fixing one point and looking at the different valuations of it, you can instead fix one valuation over any given prime, one copy of the algebraic closure of QP, if you like, and vary A, take the Galois conjugates of A. Yeah, it leads to the same number. But it's a very nice way of visualizing it. So you have the rationals, you have Q2, Q3, or the algebraic closures of these, and you have the reals. And then you have a point of your number field, and it kind of has a specialization to the variety over every prime, but you don't take just it. You take the Galois orbit, and again you get something looking statistical. It's in whole orbit. Maybe K is very large degree, so it's a very, very large finite set, and it may have, you know, you can count in what regions, in what two-adic or three-adic or real regions have how many points. You get a kind of measure, a kind of...
What is Y here?
Again, like here, it's a sub...
X also somewhere?
Yeah, Y is a subvariety of X, I think. Where is it? Where's Y? Oh, yeah, it's the same. I'm talking about the same formula all the time and just what the interpretation looks like. And the idea in both cases, either you have a very large number of points, a Galois orbit, or else you have an irreducible curve which goes all over the place. And so it's a kind of statistical situation, but not entirely random. It's not going to behave like a randomized, like a purely randomized local thing. There's also, you know, it is after all a Galois orbit, or it is an irreducible curve, and they're tied together. And in fact, in working on it, there's a very, very large amount of work involved in understanding the adelic statistical theory. And there's a little bit left over on the side of the way they're tied together. And okay, you have to play with both parts. Yeah?
That really does not depend on the Q with the algebra of the copy of the p-adic algebraic numbers.
It's not, because you take a Galois orbit. So that's what I'm saying. In other words, officially what the formula asks you to do is not to look at a single embedding into the complex numbers, for instance, but to sum over all of them, okay? But it's the same thing to sum. You have a point A, so it comes to the same to sum some expression depending on this point over all complex embeddings. Okay? Suppose you're trying to see if the point lies within the unit disk or not. Okay, it comes to the same thing to count how many complex embeddings are such that the point goes into the unit disk, or to fix one complex embedding and to ask how many elements of the Galois orbit. And it's easier to visualize because it's somehow easier to have one complex field. Okay. Okay, so one of the hopes is to have some kind of nice mechanism for similar to Axe-Cochin, but in the global setting. And how is it going to work? Well, you see Q is not really one GVF because of the same issue that I said before with curves. You can decide on what weight you give a point. So the weight of P is going to be log P, but multiplied by some constant that you can choose. And if you choose that constant to go to 0, then the weight of any particular valuation goes to 0. Okay? So we take an ultra product of renormalizations of Q such that you lend the primes smaller and smaller weight. You take the ultra product. In the ultra product, still the height of, there are going to be elements of height 1 because you have Losch's theorem and you had elements of height 1 before. But the thing that gives them height is going to be non-standard primes. Each particular standard prime is not going to count anymore.
This is an ultra product over all the renormalizations?
Yes, yeah. So you pick, exactly. So you take an ultra filter, if you like, on real numbers approaching 0. Okay. And you take Q of R, really we're going to consider Q bar, but let's say Q of R, and you take an ultra product. Now it's a continuous logic ultra product. So what it actually means in terms of usual ultra products is that you take the usual ultra product, you consider only elements whose height is bounded by some standard integer. Okay? So you throw out all the elements of infinite height. And then that's it, except we're going to obtain non-standard real values for our questions, and you just take the standard part. The height restriction is going to make sure that we get bounded real numbers. We take the standard part. So this is the notion of ultra product here. Okay. And still, Losch's theorem is true for formulas in the sense of continuous logic. Yeah. And Q becomes a constant field, right? So previously, we had arithmetic information about Q, but when we renormalize, we take the ultra product, we get something that looks like a function field. And indeed, if you pick in it some t of height 1, and you take the algebraic closure of Q of t, with normalization 1, but it's no longer the normalization of Q. Q is normalized by 0 now, but t has valuation 1, has height 1. Okay, then indeed this function field is going to be existentially closed within this ultra product of Q bar. So therefore, you get some kind of bridge between number fields and function fields. And I'm going to give 2 examples of this bridge. So the first question, I pointed out that in the algebraic integers, the main phenomenon is gluing. In some sense, the only one. These are the main axioms. What happens when you have the product formula? It is clearly no longer true that you can just glue freely. For example, if you're looking for rational, which is an integer modulo p for each p, so it's an integer, and at the same time it has absolute value less than a half over the reals, you cannot do it, right? There's no free gluing. Sorry? What about it?
The lattice is in Q to the n?
Yeah, in Q to the n. I just take it in Q to the n for simplicity. Yeah, so this kind of question about gluing came up in 19th century number theory, where it became important to have different constraints for different primes. And the somehow axiomatization of it, in some sense, is the geometry of numbers by Minkowski. And here, and there's things called Minkowski's first theorem, Minkowski's second theorem. And here's the first theorem. So I'm going to do it in Q. I'm going to concentrate on the global field itself, really Q bar and so on. But take a lattice in Q to the n, meaning, well, it's a copy of Z to the n in Q to the n. All right? So you can adjust it. Well, it has some basis, but OK, you can. OK. So take some lattice. And on the other hand, in the reals, take a convex symmetric bounded subset. I might point out that this lattice, you can take the p-adic closure of it, or you can take the ZP module generated by it, and you also get a nice compact subgroup of QP to the n for each n. So you have some local condition for each p, and then you have some condition on the reals. On the QPs, it's linear. We really get a subgroup. On the reals, well, it's not exactly a subgroup, but it's an approximate subgroup. And the correct factor for approximateness is 2 to the n, right? If you take a cube in n dimensions and you add it to itself, then you get something which is bigger, but only by a constant number of times. And yeah, and what Minkowski tells you is that if the volume in the real part is sufficiently big compared to the volume, what is called the volume of the lattice, but really should be the co-volume of the lattice, the volume of a fundamental domain, then the intersection is not just 0. Then there's a vector which is in the lattice and in the domain. And the proof is very, very easy once you have modern measure theory and so on, and some people might be familiar with it from approximate subgroups and Hrushovski's method. Anyway, I'll leave you to think about it, basically. They're not, OK. This is the basic theorem. And you can think of it p-adically. So if you think about it p-adically, you have a p-adic lattice. It means, well, it's a finitely, it's a free modulo over ZP for each p. You also have a compact set in the reals. And now the condition on the volume, if you think about it, the volume is just some kind of determinant of something. And the product formula tells you that the determinant, well, being is also the product of its p-adic. The absolute value of the determinant is the product of its p-adic valuations. So you can measure the volume p-adically if you want, and then there's an inverse. So they all come out. All right. So yeah, so the volume just becomes the product of all primes of the p-adic volume. And this is just a restatement of the same theorem idealically. OK, what do we get? So this is a true theorem. And therefore, if we take an ultra product, we're going to get another true statement. What is this statement? Well, the volume, I was using it in the multiplicative sense. But we're going to work additively. We're going to take minus log, OK? So that we just take minus log. But we also renormalize everything, remember, by r. So when I say log, the correct log to take is log to the base of r. Or you take log divided by log r. And that means that the number of 2 to the n becomes 0. It just approaches 0, right? All these factors that you get in the Archimedean prime becomes 0. So the corollary of that is that in the ultra product, if the valuative volume is negative, meaning that in the factors it would have to be bigger than any given standard number, in particular bigger than 2 to the n, then there exists a non-element, there exists a non-zero solution. There exists an element which is constrained in that way p-adically for every p. So this is somehow supposed to be the axiomatization of the gluing principle. Well, when Minkowski did it, you could only do it by practically checking whether you can prove enough theorems this way. But in the non-standard setting, it's correct. So Itai beautifully found out a theory of fullness, which is exactly this principle. So to be full is exactly the principle which is written in this corollary. And it turns out to be exactly the axiomatization of existential closedness with respect to a single variable. Yeah, so if you completely ignore these things and you just ask yourself over an algebraically closed field, when can I solve an equation in one variable? Well, over an algebraically closed field, it's going to be, right, polynomial split is going to be a linear or at least affine equation, and you can try to find out what are the GVF constraints, and basically it's the product formula. So basically, why not? Why not add a solution with given p-adic constraints? Well, maybe the only possible reason is that there's already something too close to a solution. This is something, okay. So in fact, it's an axiomatization of existential closedness. Okay. So you can get it this way. So this is already beginning of a hint of how this axiomatization, something is right with it. I mean, it shows you some non-trivial history, if not yet future, of mathematics just by investigating a simple logical question. Incidentally, we still don't know whether this might be a sufficient axiomatization for curves. I might say something about it at the end. It's quite a delicate issue, and in particular, existential closure for curves, whatever the correct axioms for it are, includes some very non-trivial mathematics, in particular, Rumely's theory of capacity on curves. The theory, well, it's exactly the theory of when you have local constraints, but on a curve for every prime, when can you expect to get algebraic integers in them? Okay. I might mention something later on. Yeah. Okay. Okay, so now let me start giving some examples of formulas. So I'm going to start with, I'm going to give some unary formulas, viewed as unary formulas, even if they lie on a variety, and then some binary formulas. Yeah. So Anna, until when can I mean,
We started a few minutes late, so say 10:25.
10:25? Okay.
That might only 55 minutes.
All right. Yeah, good, thanks. Okay. So we talked about the height of a single element. For a non-zero element x, okay, so this is the classical case. Anyway, we can define height of x equals 0. This is a certain subgroup. It's a definable subgroup of the multiplicative group. And in fact, in some sense, it's the only one. When you say something is definable, infinitely definable, you're implying that it has bounded height in this framework. And if you have any definable subgroup of elements of bounded height, it means also that any power of the height remains bounded, which means they must have height 0. So in Q bar itself, you only get roots of unity. But of course, when you go to other GVFs, by compactness, you get some other structure, and it's interesting to study the induced structure on it. And amazingly, every time you look at anything, you keep seeing these phenomena of I don't know, geometric stability theory. Well, you have this, it looks like a U rank 1 structure. There's a unique generic type, and okay, beyond that you get it. Okay. And the induced structure of it is just the pure group structure. Yeah, I'm not, so okay. These are non-trivial statements, and to some extent they include to a very large extent they include non-trivial statements made by geometers earlier. In this case, Bilu, and partly out of ignorance and partly out of time, I'm not going to be able to mention all the things that we cover, but there's a vast amount of this, and this is part of the point, was known to geometers. An analogous example on an elliptic curve, once again, there's a notion of height. You can take your, you can embed it in projective space and take your notion of height, or just take, take the same naive notion. As I mentioned before, it doesn't behave so well, but there's a standard way to make it behave well, namely, you multiply by n, you notice that it behaves almost quadratically with n, and you renormalize to get something nearby which actually behaves well under multiplication by n. So this corrected height, the canonical height, is also definable in the sense of continuous logic. And a similar thing you can do with any abelian variety. Okay. Okay. So here one sees a very similar picture to, partly conjectural, partly known picture, very similar to what we're familiar with in other structures like differential fields. You get certain finite rank formulas that seem to satisfy Hilbert's conjecture. It's really extraordinary how you get it in difference algebra, differential algebra, here in global algebra. Okay. One thing which is not completely known as part of this picture is the Bogomolov conjecture, namely that on these minimal subgroups, there should be a unique generic type. Part of that is the intersection with subvarieties. That seems to be the hardest part. The expectation is that, like in things like Mort-de-Lang, the intersection with nonlinear subvarieties should be just a finite union of proper subvarieties. Essentially, it should not contain nonlinear things. And it's very largely known, but not completely known in the classical cases.
But here you're still working for this continuous setting.
Yes. Even though you're working in this continuous setting, it turns out you have things which are, you have equidistribution theorems which tell you that the adelic part, the statistical adelic part where you get to say something about measures in Berkovich spaces, disappears. In other words, once you lower the height to 0, it behaves uniquely. And the remaining question becomes about intersection with subvarieties. Yeah, so there's something that okay. Beyond the adelic part and beyond intersection with subvarieties, there's one more part which also behaves well, which I'm not going to have time to describe. All right, so we discussed GM, or an abelian variety, and a small definable subgroup contained in it, the induced structure on it. Well, you can also look at the quotient, and this also plays a very important role in what comes later, which I won't really have time to discuss. In the case of the multiplicative group, it's like looking for valued fields at the multiplicative group modulo the multiplicative group of the valuation ring. In other words, you get the value group. And here you get some kind of analog of the value group, which is a Banach lattice. If you take an abelian variety, what you get is a definable, or if you like, hyper-definable, so continuous logic definable. You get a definable Hilbert space, namely this canonical height induces a norm, which is in fact a Hilbert space structure. And once again, I'm not sure I'll have time to get to it, but it plays a very essential role in understanding arbitrary formulas. And okay, it leads immediately to interesting, it has a very strange structure in some sense because it's a Hilbert space, but well, you get embedded curves in it, which look discrete and nevertheless generate the Hilbert space in finitely many steps. It's an amazing thing, which I won't have time to talk to. All right. Okay, so I'll just mention in one word, maybe I have time to read, a second example of a transfer principle. This time, earlier I transferred Minkowski's theorem from number fields to function fields, and now I'm going to transfer some known cases of the function field Bogomolov conjecture to, well, you could do it with any known case if it's known in the GVF sense, but I'm going to translate a particular known case due to a student of Rumelik, Shinkir, to number fields. Well, the number field case of Bogomolov's conjecture is also known, but what you get is not the number field case of Bogomolov's conjecture, but you get a uniform version in which the height, you get that elements of not so small height, yeah, but just height, which is, let's say, 1/10 of the height of the abelian variety itself. So you think of a family of abelian varieties varying. So the height of such an element, this height restriction will be enough to make sure that it intersects it intersects nonlinear curves in only finitely many points, for instance. I made this slide for a talk 2 years ago in Orsay. I think that there's not much intersection in the audience, it seems to me. And I had no idea that such things are actually considered even in the number field case. Recently, Tom Scanlon, who had similar ideas somehow, pointed out to me that in fact, yes, I mean, people do consider such things, and they have bounds which in some cases are similar bounds, and in some cases are conjectural. Okay. Anyway, they don't match exactly, and it still makes a very interesting connection between the two things. Yeah, so now I have 2 minutes to talk about binary relations. I need to do it because I need to correct something that I said. For those of you who were in the conference in Bedlevo, I need to correct something that I said. So here's some binary relations. Remember, this is this mean distance between two things. And to give a simple binary relation, let's take the diagonal. In fact, you can do it with any correspondence or something. But let's take the diagonal. Take a variety x, consider the diagonal, and consider the mean distance from the diagonal in this sense. Well, that gives you a formula which might take value 0 or might not take value 0. What kind of relation does that give between 2 points? And I'm interested in Zariski dense points. I'm interested in pairs A, B, which are not on any proper subvariety. Okay, so in the case of P1, you do not honestly get a new binary relation. You see, in that case, if you look at x minus y, the zeros of that are the diagonal, and the poles of that, well, there's one pole at one factor and one pole at another factor, and it shows you that, okay, this apparently, so the fact that it adds up to 0 shows you that actually you can compute this distance in terms of just the heights. So there's nothing new. If you take a curve, it's already quite interesting, and this I even understood, I won't have time to discuss, but it's controlled by this Hilbert space that I discussed before. And in particular, so it's really, it looks like an angle. If you look at this minus the heights, it looks like it behaves, the universal theory, if it looks like the cosine of an angle, that's what you get. And in particular, it's again a stable relation. Let's not look at curves, let's look at varieties of dimension 3 or more. Well, in this case, you get into some combinatorics. So you have a lemma saying that there exists a polynomial in many variables. You're led to look into a polynomial of many variables, which vanish on all the diagonals, but their degree is not n squared. It's not the number of diagonals. It's substantially less than the number of diagonals. And okay, so the proof of that can be done by dimension counting. And what this shows is that this graph that you get by this relation, saying that the mean distance to the diagonal is non-zero, let's say greater than or equal to some epsilon, well, it resembles a bit the graphs that you get by trying to build examples of stable half zero categorical theories. Namely, you cannot have too many edges on a subset of size n. In this case, the constraint is not linear, but it's subquadratic. And that's enough to make sure that you have a stable relation once again. And furthermore, any two-dimensional, so I've covered curves, I've covered three-dimensional varieties. There's only two-dimensional varieties left over, and actually they're reduced to P2. And here I have to admit, we don't know what happens for P2. We don't know the answer to this combinatorial question. It seems to be a fairly delicate combinatorial question, and it may not even be the right way to approach it. So I retract. In Bedlevo, I claimed that I can prove stability for all quantify-free formulas, and I was careful enough to call it a small t theorem. You see, calling it a conjecture would glorify it too much. You need much more evidence for a conjecture than for a theorem. But it was explained to me that you say small t. Anyway, it's become even smaller, this T, for the time being. This is what I do know. There is a canonical amalgamation of GVFs, and which I will not describe. It involves all this structure that I said before, the local, statistical local structure, and the Hilbert space structures. It's very canonical, and two things are freely amalgamated if and only if each one is finitely satisfied, the types are finitely satisfiable in both ways, that's fine. But one additional thing, this one specific formula concerning the diagonal to P2 has not to hold in order to have the free amalgamation. So it resembles simple theories. It resembles the picture we had at the very beginning of simplicity, which maybe needs some correction. But anyway, the picture that a simple theory is a stable theory plus some white noise, which doesn't interact with anything, but you can just superimpose it, some kind of random graph on top of forking. We don't know if it actually exists or not. It might be that this formula is also stable, in which case you can state that every quantified free is stable. Okay, so I'll stop here. Thank you.